Hi students, this is Mr. Bob, and this video you're about to watch is about nuclear fission and nuclear reactors. It's under subtopic 7.2. And so before watching this video, you should have watched the 25-minute section regarding Lisa Meitner in that movie, Einstein's Big Idea equals MC squared. You can get it on YouTube. I gave you a link. You should have some focus notes set up wherever you take your notes and have a colored pencil or highlighter ready. And again, my strong recommendation is about 24 to 48 hours after watching this video, you should review the Giancoli sections in your physics textbook that I've laid out and revisit these notes and add to them, fill in, add, group, chunk as necessary, and especially highlight any points of confusion that you might have. So, and just recommendations while you take notes, again, avoid the mindless copying, just selectively write down and abbreviate. And if there's sample problems, make your brain think about it, pause the video. And if you're still confused, make sure you identify those points and you follow up with me or a classmate to get your points of confusion cleared up. So we have two essential questions for this video. The first one is, what are the factors that impact whether the products of a nuclear fission will cause an additional fission? And the second question is, how is a nuclear reactor different than a nuclear weapon, and how is the chain reaction controlled within the reactor? So let's jump right into it. When we talk about nuclear fission, what we're talking about is we start out with a large nucleus, and it somehow splits up into two smaller or daughter nuclei. And so here's an example I just want to show you. Don't copy down this equation because we're going to generalize it here in a second, but watch this animation. Notice I have that big nucleus, the nuclide, and that neutron came in and boom, caused it to become unstable and break up. In the Meitner videos, some of the historians talk about the water drop model, and that's a good model to think of. The fact that you have this big water droplet, big nuclei, you can think of them as big water droplets, then you just get this smaller droplet that comes in and makes it just unstable enough that it kind of splits apart. Okay, so the important thing here to notice is that not only do you have the two fission fragments, but you also have additional neutrons that basically go on to do some other things that we're going to talk about here in a second. I want to go back to something we talked about in the previous video, which is this binding energy per nucleon curve, because this is important in the following. If you remember, on the y-axis, we have plotted the binding energy per nucleon. Remember that you can think of it as the amount of energy required to be put into the nucleus to extract one nucleon on average. And then you have the size of the nuclides on the bottom here, the size of the nuclei. And notice what we have over here all the way to the right is uranium-238. And remember what we said, one of the key ideas is that as the binding energy per nucleon of a nucleus increases, its stability increases. And that in a nuclear reaction where energy is released, the binding energy per nucleon of the products is greater than that of the reactants. So if you notice in this diagram, if you're here as a heavy nucleus, in which direction, what's going to have to happen to you in order for the binding energy per nucleon to increase? Notice you're going to have to move in this direction, meaning you're going to have to split up into smaller nuclei. Okay, and that's essentially what happens in this graph. If you look at what's going on, this graph kind of shows you or dictates to you what happens in nature. Larger elements tend to undergo things like fission, because when they do that, larger nuclei, I should say, those become smaller nuclei which have bigger binding energy per nucleon. In contrast, on this left end, you can see here hydrogen and helium, if they're going to get greater binding energies per nucleon, that's not going to happen for them by fissioning, meaning that they would have smaller fragments. They have to combine in order to create larger and larger nuclei. Okay, so in this side of the binding energy per nucleon curve, what you get fusion that tends to happen in nature, and that causes larger nuclei to be created and energy to be released. Okay, so let's go back to something that was said in the video by Otto Frisch, Lisa Meitner's nephew. If you remember at one point where they were out with the snowshoeing, they were talking about the fact that in a nuclear reaction, if a uranium-238 nuclide were to split up, then the difference was 1/5 of the mass of a proton. And so I just want to go through this little exercise. If we take the mass of a proton, take 1/5 of it, so there's 1/5, and if you remember, the mass of a proton is 1.007276 atomic mass units. Okay, we'd get a number for that, but what I really want is I want to figure out how many mega electron volts is that. And if you remember, we have that conversion where one atomic mass unit is 931.5 mega electron volts. So if you want to pause the video and multiply that in your calculator really quickly, I recommend you do that. Okay, when I do it, I get 0.2 times 1.007276. I get a number that is roughly 187 mega electron volts. Okay, and so this is where in the video there's that big aha moment, and he says, "Well, what's going to provide the energy?" And basically, the answer is that what happens is in that reaction, some of the mass of those starting nuclei is converted into energy. So the general sort of equation that you want to kind of have in your mind for a nuclear reaction is this one, where notice in this case we have uranium-235, and I'll talk about that more later on, but you'd have a uranium atom, absorbs a neutron and becomes unstable, becomes a uranium-236 atom, but only for a fraction of a second. And then that fission splits up into two smaller fission fragments. That's what those are called. FF1 is just short for fission fragment 1, fission fragment 2. And then the third thing is really important, 2 to 3 neutrons, okay? And so notice what happens here is the mass of the products is less than the mass of the reactants. And so energy is released, and it's approximately 200 mega electron volts, 187, 200 is close enough. And so two things are important here. The first one, which you can see there, is if each of these neutrons splits subsequent nuclei, then we have what's called a chain reaction. But the other important thing to remember is that going back to the binding energy per nucleon sort of idea, is that the binding energy per nucleon of those fission fragments is inherently going to be greater than the binding energy per nucleon of the uranium-236 nuclide. It has to be, and that's how the energy is released, because more energy is released when those fission fragments are created from the uranium-236. This is kind of a visual of what nuclear fission chain reactions might happen. Obviously, you get neutron coming in to that uranium atom. Coming out of the uranium atom is 2 or more neutrons, and those may or may not go on to cause future fissions, and we're going to talk about that here in a second. But you can notice the chain reaction is that it grows with time. Under the right circumstances, it can grow pretty significantly, as you can already see here, if this were to continue. Now let's talk about something really important, which is the difference between nuclear bombs versus nuclear reactors. So in a nuclear weapon, what the designers want is an uncontrolled nuclear reaction. And that's the desire because they want an immense and very rapid energy release. So that might look something like this, like you just saw in the last image, where you get one fission causing multiple fissions to occur, and all of this occurs within a fraction of a second. Okay, this is what we call an uncontrolled reaction. Now, in contrast to that, when we're trying to design a nuclear reactor, something that's going to generate heat and then ultimately going to be used to generate electricity, we want to control that nuclear reaction. And so the goal here with a nuclear reactor, and what we're going to spend pretty much the rest of the time talking about, is this, where you still get those multiple neutrons coming out, but some of those neutrons are absorbed, and only a small fraction of those neutrons go on to cause additional fissions. Or I'll tell you kind of what we want to get here in a second. So the key idea here is, in a nuclear reactor, some of the product neutrons are absorbed by other material before they cause another fission. Whereas in contrast with a nuclear weapon, many of the product neutrons go on to cause other fissions, and you get a ballooning of that chain reaction. Okay, so when we talk about a nuclear reactor as part of a nuclear power station, what's going on here? Remember, in uranium-235, you get somewhere between 2 and 3 product neutrons. And so these neutrons have a wide range of kinetic energies. So if the kinetic energy of the neutron is too high, it won't cause further fissions. So if you notice here, boom, that neutron is going way too fast, does not cause a fission when it passes that uranium-235 atom. The other extreme is not good also. If the kinetic energy is too small of uranium-235, of a neutron, when it hits a uranium-235 atom, it will not cause a fission. So you just have to have the Goldilocks approach, right? You have to have the neutron that's just the right speed, okay? So, so one of the ways we control the chain reaction, one of the ways we make the chain reaction able to happen is shown by this slide, which basically what I want to make you realize is when you get a chain reaction, most of the neutrons that are coming out of that uranium splitting are really fast. They're going way too fast to cause further fissions, okay? So notice this is kind of an example distribution. They're somewhere between 1 and 2 mega electron volts on average. But in order to cause an additional fission, that neutron has to be moving at a fraction of an electron volt. So in other words, like 1/1,000,000th of the initial kinetic energy. So how do we slow it down? Okay, we slow it down by basically putting something that's called a moderator, such as graphite, light water, or heavy water. We slow these fast neutrons down enough so that they can basically go on to cause further fissions. Okay, I'm going to talk about fuel rods, the fuel rod area here in a second, in a little more detail. But the big idea of this slide is you have to understand that in a nuclear reactor, in addition to the fuel, the actual uranium fuel, you have a substance called a moderator. And that moderator is there, and it's meant to slow down the fast neutrons that are generated by a fission so that those neutrons can then possibly go on to cause further fissions. Okay, so that's one way we control or allow the chain reaction to happen. The second piece we're going to talk about in the next slide. Okay, and this next slide, what I want to show you is I want to show you these red sort of rods here, and they're called control rods, okay? And so control rods are absolutely vital in a nuclear reactor. Control rods are made of these rich neutron-absorbing materials, and they're inserted strategically, geometrically in the reactor in, basically you can see that they're spread out pretty evenly in a reactor, so that they can be very exactly and precisely moved in and out of regions of the reactor to cause the chain reaction to either increase in a certain area or decrease, okay? So if you raise the control rods, because these control rods, they absorb some of those neutrons. They have a big cross-sectional area to absorb neutrons. And so if you raise those control rods, then that's going to increase the reaction rate. That's going to increase the number of neutrons from a chain reaction that go on to cause a further chain reaction fission. But if you insert the control rods into the core, deeper into the core, then that will decrease the reaction rate. Okay, so what are control rods made of? They're generally made of things like cadmium and boron. Again, these are things that cause, that have what we call have a rich cross-sectional area for absorbing neutrons. So a logical question you're probably asking, or you would want to ask, and you would want to know the answer to, is what do we do with the energy that the fissions create? So great, we have these fissions occurring, we have a bunch of energy being created in that core area. How do we get something useful out of it that society can use? Well, that heat that's generated there, basically, what you have is you have water or some other thermal absorber that can be circulated, okay? And so in essence, notice these control rods are going up and down. This would never happen in a reactor, by the way. This would be way too much motion, but this is for exaggeration purposes. But notice what you just saw there. In this case, this is water that I'm demonstrating in this little graphic. That's water that's being circulated through that core where the fissions are happening. So what's happening? The water is absorbing some of that heat energy, and it's gaining more energy, gaining more kinetic energy, raising its temperature. So here's a key idea that I want you to keep in mind. Pressurized water reactors, this is kind of the prototypical reactor that we're talking about here, use water for this thermal absorber. And this is definitely by far the most common type of reactor that's used today in commercial power plants, and also, by the way, in military uses as well. It's not the only one, but it's by far the most common. And this is also the kind of reactor that IB expects you to be able to describe and explain its operation. Okay, so we're talking about pressurized water reactors here. Notice, I do want to make sure you realize that there are other designs out there that don't use water as the thermal absorber. For example, there are some reactors out there that use liquid sodium. Those are generally not so much in the US, they're usually in foreign countries. Okay, so let's talk about a nuclear power station. And there's going to be a lot in this slide. So let me just kind of walk you through it here. So here we have this part over here that I'm circling. This is the part we've been talking about for the past several slides. That's where the uranium is. That's where the moderator is. That's also where the control rods are. You can see the control rods here. So these are all contained in what's called this primary loop. And there's And you can see the red stuff is the thermal absorber, which in our case is water. Okay, and what we design, how we design these reactors, these pressurized water reactors, as the name implies, notice there's this little device here called a pressurizer, which all you need to know about that is that that causes the pressure, that maintains the pressure really high in this whole primary loop. And why do we do that? We do that so that the water can stay in liquid form, because the higher the pressure, the higher the temperature the water would need to be in order to boil. Okay, so we keep this pressure so high that the water never even gets anywhere close to boiling. And so what we do then is we circulate that water that's at a very high temperature and we send it through a heat exchanger, which is basically, oftentimes we call it a steam generator. And as the name implies, it generates steam. How does it generate steam? Well, through these other pipes that you can see here that are in blue, there's a different set of water that's being run through right next to this very hot water coming out of the reactor. And so what happens, we know, thermal equilibrium being what it is, that hot water is going to pass off some of its energy to the colder water. So much so that the colder water, which is at a much lower pressure, over here we have a low pressure, right? It's not pressurized like the primary pressure. So in here, in this vessel, you're going to get so much temperature, so much energy added to the colder water that the colder water is going to boil. And it's going to create steam, and it's going to create superheated steam. Superheated steam being a gas, it's going to move out of the top, it's going to come over here and be routed through a turbine, okay? And this is a turbine that will spin, and well, I'm not going to talk about this too much more today, but basically this turbine spins, and out of this other end, you get electricity. It's called a turbine generator. And so all you need to know for this purpose, for this lesson today, is that steam spins this turbine, causes electricity to be generated. The electricity gets fed out to a power station, and notice, boop, you get lights to light up your family, your iPad, your everything, okay? And notice just, I'm not going to talk about this. I don't really think there's too much to be said here, but the water gets returned here through a condenser. It gets cooled down from, excuse me, the steam after exiting the turbine gets cooled down enough so that it returns to liquid form and it gets pumped back into the bottom of the steam generator. Okay, so we have a joke, a bonus joke. Here we go. What did the sign say on the abandoned nuclear reactor? Gone fishing. I bet you weren't expecting a joke at the end of this video. That's a bonus joke for all of you out there. All right, so those are the two essential questions. I hope you're able to answer them, and I'm sure I will talk to you soon in class. Thanks, everyone.